Students, perhaps you'll remember that I have left out in that slide in my earlier video. Now, before proceeding, I want to recapitulate it once again. Number one, I was discussing about the electrical properties of material. And for that, I have discussed the Ohm's law, V is equal to IR, where I is the current, V is the voltage, and R is the resistance of the conductor. The resistivity and electrical conductivity were also discussed. Now, with that, we have came to a band theory, and I have shown you that the metals, they have no gap, they are overlapping between valence bond and conduction bond. But semiconductors have a considerate gap between semiconductors, that is between valence bond and conduction bond. And insulators, the gap is much more higher. That is why the electrons cannot jump on easily. So metal is a good conductor. The semiconductors are not as good conductors, but they need some extra charge. And the insulators are bad conductors, and that is why they are used in different ways. So that is the conduction level in metals, as I have shown you already, the electrons and the holes, and the concept of holes as a charge carrier comes into the semiconductor field. And for that we have two type of conductivity as well, and this is the dopant, where free electrons and free holes are created. One is N type, another one is P type. And with that we have discussed that part also. That is a donor state, which is, and then acceptor state. And in the extrinsic conductivity also discussed, as effect of temperature was discussed, and effect of temperature with germanium and silicon were discussed in my earlier weights. And this is the extrinsic semiconductor. Now the effect of temperature in a stasis semiconductor is as the in the low temperature region known as freeze out region, the charge carriers cannot be excited from donor level to conduction band due to insufficient thermal energy. In the intermediate temperature range, almost all the donor atoms are ionized, and electron concentration is approximately equal to the donor content. This region is known as extrinsic region. In the high temperature region, sufficient thermal energy is available for electrons to get excited from the valence to the conduction band, and hence it behaves like an intrinsic semiconductor. So that is presented one for silver, copper, gold, aluminum, nickel, iron, and platinum. The conductivity and resistivity charts are shown here below. Again for silicon, germanium, yes, and all the band gaps with conductivity are shown in the table. And this is an important part, the dielectric property. A dielectric material is an insulating material which can separate positive and negatively charged entities. Dielectric metals are used in capacitors to store the electrical energy. The capacitance C is related to the charge stored, Q, between two oppositely charged layers subject to a voltage, that is C is equal to Q by V. If two parallel plates of area A are separated by a distance in the vacuum, then C is this one. The permittivity of vacuum is that much. If dielectric material is present between the plates, the permittivity that is shown here. The orientation of a dipole along applied electric field is called polarization. It causes charge density to increase over the vacuum due to presence of the dielectric material, so that D is equal to that much, where epsilon is the electric field. D is the surface charge density of a capacitor, and also called dielectric displacement. This is the type of polarization. There are four types of polarization: electronic, ionic, orientation, and space charge, that is interfacial. The electronic polarization is due to displacement of the center of the electron cloud around the nucleus under the applied field. Ionic polarization occurs in ionic material as the applied electric field displaces the cations and anions in opposite directions, resulting in a net dipole moment. So here cations and anions are actually doing the polarization part, and that is why it is known as ionic polarization. There is orientation polarization can only occur in materials having permanent dipole moments. The rotation of the permanent moment in the direction of the applied field causes the polarization in this case. Space charges polarization arises from accumulation of the charge at interfaces in a heterogeneous material consisting of more than one phase having different resistivity. So these are the four types of polarization. We were discussing about dielectricity and dielectric property, capacitance and polarization, and types of polarization. Now this is another one, a new term for you, that is ferroelectricity. Ferroelectricity is defined as the spontaneous alignment of electric dipoles in the absence of an external field. The spontaneous polarization results from relative displacement of cations and anions from their symmetrical positions. Therefore, ferroelectric materials must possess permanent dipoles. Examples of ferroelectric materials are BaTiO3, Rochelle salt, NaKCl4, H4O6, 4H2O, potassium dihydrogen phosphate, KH2PO4, potassium niobate, KNBO3, lead zirconate, titanate, ZrO3, TiO3, whole Pb. These materials have extremely high dielectric constants and relatively low applied field frequencies. Hence, the capacitors made from ferroelectric materials are smaller than those made from dielectric materials. So that is the positive part. Another one is called piezoelectricity, is defined as the conversion of electrical energy into mechanical strain and vice versa. It arises due to polarization induced by external force. Thus, by reversing the direction of the external force, the direction of the established field can be reversed. That is, the application of an external electric field alters the net dipole length, causing a dimensional change. Application for these materials includes microphones, ultrasonic generators, sonar detectors, and mechanical strain gauges. Example is barium titanate, lead titanate, lead zirconate, that is PbZrO3, ammonium dihydrogen phosphate, NH4H2PO4, and quartz. These are the examples of piezoelectric materials. So this is Piezoelectricity defined as conversion of electrical energy into mechanical strain and vice versa. So I think that is the end of the lecture, and these are the questions. What is Ohm's law? What is resistivity? Briefly explain the band theory and electrical conduction. What is Fermi energy? Why are the metals highly conductive? Briefly explain the conduction mechanism in metals. These are the questions. What is the difference between band structure of Cu and Mg? How is the conductivity of metals affected by impurity level? Is it good or bad? What is the role of dislocation on conductivity of materials? And we have to explain it with pictures and diagrams. Why does the metallic conductivity decrease with increasing temperature? What is the typical band gap in semiconductors? What is intrinsic semiconductivity? So that the conductivity of an intrinsic semiconductor is this one, the equation. We have to show that. What is the effect of temperature on extrinsic semiconductor? Name some of compound semiconductors. Calculate the electrical conductivity. What is dielectric constant? What is polarization? How many types are there? What is ferroelectricity? What is piezoelectricity? And we'll give some examples of ferroelectric materials, give some examples of piezoelectric materials, and the numerical as well. Please look at the numerical where after that we should close the chapter. So this is the electric materials, the electrical property of the material. What are the acceptor and donor levels? Okay, I think this is the end of the lecture, and I thank you all. And please study well and